Lewis structures, hybridization, and bond angles. So in this video, we're going to be talking about electronic and molecular geometries and what impact that has on the angle, the bond angle within the molecule. So Vesper theory says that electron domains repel each other. This is the Coulombic force. Like charges repel each other. So the most stable arrangement of electron domains is going to occur when they are as far apart as possible. So this leads us to these different bond angles that we associate with different numbers of domains. So an electron domain is going to be either a lone pair of electrons or a bonding pair of electrons. So where do we get these hybridized orbitals from? So if we have two domains here, that's going to be S and P. So think of S as one domain and P as another domain. 3 domains is sp2, 4 domains is sp3. So if you're kind of adding that up, that's 3 P's and 1 S, which makes 4 domains. If you wanted 5 domains, then we need to go into the d orbitals and start adding those in, and 6 domains and so on and so forth. Now, we have bond angles associated with 2, 3, and 4. We also have them with 5 and 6 and so on, but these are the main ones that you should know. So if you have 2 domains, the farthest away they can get from each other is going to be an angle of 180, and this is where we get the linear electronic geometry. Now, electronic and molecular geometries are different in that the electronic geometries considers how many electron domains there are, whereas molecular geometries are simply based on the atoms that are present. So, for example, something that has a linear electronic geometry, there's actually 2 molecular geometries that are associated with that one electronic geometry. For example, if you look at trigonal planar, this refers to 3 electron domains. So either 3 bonding and non-bonding pairs, something like that. So we have, if we have all of those atoms, we get trigonal planar. Well, what if we only have 3 of those and one of those electron domains is a lone pair? That's where the bent shape comes from. So let's start with this CH2Cl2 molecule here. So let's start by drawing our Lewis structure. I know that carbon is going to be my central atom here because it can make the most bonds. So I'm just going to go ahead and start by connecting these with some single bonds here. So the total number of electrons that I have here, let's see, I've got 14 from the chlorine, plus 4 from carbon, so that's 18, and then 2 from the hydrogen. So I have 20 total, and I've just placed 2, 4, 6, 8 of them, which means that I now have 12 electrons that are remaining. So I'm going to start by placing these where I can. I can't put any on hydrogen because that guy can only hold 2 electrons total, but I can put 6 on each of these chlorines, and that's going to take care of the 12 remaining electrons here. So we can check our formal charges, we can check our bonds, everybody's going to be stable here. So this gives me an electronic geometry that is tetrahedral, and that's because there are, on that central carbon has 4 things that are bound to it. So we've got a hydrogen, a chlorine, and a chlorine. So those 4 groups there give us the tetrahedral shape. So as far as hybridization here, I've got 4 orbitals here, 4 bonds here. So this is going to be my sp3 hybridization. Now the shape of this is going to be the same because all of these electron domains here are representing atoms, and they're not representing lone pairs. So the shape is the same. So anytime that we have 4 electronic domains, the bond angle associated with that is going to be that 109.5. So the next structure that we have is SO2. So sulfur is going to be my central atom. Keep in mind, sulfur has access to the third energy level, so it can hold more than an octet worth of electrons. So sulfur is going to have, what, 6 electrons, and oxygen also has 6. So that means that I've got a total of 18 electrons to play with. So I'm going to start with some single bonds here. So I've just placed 4, which means I have 14 left. So I'm going to start placing those where I can to satisfy any octets. So that's 12 more. So now I've got 2 left. And there's no place else where I can put them, so I'm just going to put that as a lone pair on sulfur. Now, if we were to check formal charges here, we're going to see that these oxygens are both -1. So the way to get rid of that formal charge is going to be to take some electrons and move them into the bond here. So I'm just going to take this guy and make him a double bond. And I'm going to do the same thing on the other side, take away one of these lone pairs. So this ends up giving us the best Lewis structure for SO2. So if you look at the sulfur, we've got a double bond, and a lone pair. So that is 3 electron domains. So this is going to be trigonal planar. So the hybridization that's going to be associated with this is going to be sp2. So what shape will this be? Well, the shape is different from the electronic geometry because in the shape, we only look at the atoms. So here we have a lone pair instead of an atom, so we end up with a bent shape. So the best angle based on that shape, is going to be 120 because that allows these electronic groups to get as far away from each other as possible. Okay, so looking at our next molecule, we have SE4. So this time we've got Se selenium, and then we've got these 4 fluorides. So that means that we have a total of 34 electrons to place here. So I'm going to start by just connecting everybody with some single bonds here. So that's 2, 4, 6, 8 more electrons, which means now we have 26 left. So I'm going to put 6 on each of these fluorides because I know they need more to complete their octet. So there's 12, 18, 24. So now I've got 2 electrons left. And the only place where I can put that is on the Se. And that's okay because Se has that expanded octet available to it. It can go into the third energy level and use those d orbitals to achieve more pairs here. Now, as far as the shape on this one, the electronic geometry is trigonal bipyramidal. And that's because we have a total of 5 electron domains. We have 4 bonding pairs and 1 lone pair. So what hybridization is this going to be here? Well, I'm looking at 5 bonds here, 5 domains. So I'm going to need my S. I'm going to need all 3 of my P's. That gives me 4 domains. And I'm going to need a d orbital as well. So what shape is this? Because one of those electron domains are a lone pair, we end up with this seesaw shape. And actually in this seesaw shape, we have 2 bond angles that are possible. So as we get into these sort of more complex hybridizations, there's more bond angles that can occur. But if you look, we can see that we have a 90, like here or here coming out at you. There's 90. But then we also have some 120 kind of going on right here. So we're seeing both of those bond angles in this particular molecule. So I've got 90 and 120. So now let's look at CH2O. So first I'm going to start with my total number of electrons. So 4 plus 6 gives me 10, 11, 12 total. I'm going to connect those all using single bonds. So that's 2, 4, 6. means I have 6 electrons remaining. So the best place for those is going to be on this oxygen. Now, if we were to calculate the formal charge on this oxygen, again, anytime you see that single bond oxygen, be suspicious because it's going to have a formal charge. So at the moment, I have a formal charge on this oxygen. So the way to get rid of that is going to be to take 2 of those non-bonding and put them into a bond. And this actually will make the formal charge on carbon come to 0 as well, because now the carbon has 4 bonds. So this is going to have a trigonal planar electronic geometry, and we've got sp2 hybridization associated with that. And the shape is also trigonal planar because all of those electron domains are bonding pairs. None of them are lone pairs. So we've got a total of 3 domains, and the angle that is associated with that is 120 degrees. Last molecule here, the way that this is written, it's CH3, then there's an O and another CH3. That is the type of notation that's used in organic chemistry, and that's denoting to you that that carbon has 3 hydrogens on each side. So the Lewis structure, we're going to start off something like this. We've got those CH3s on the left and the right, and in the middle, our central atom is oxygen here. So I've got carbon and carbon, so that's going to give me 8 plus 6 here is going to give me 14, 15, 16, 17, 18, 19, 20 electrons total. So I'm going to start by connecting everybody just using some single bonds here. So how many electrons is that? 2, 4, 6, 8, 10, 12, 14, 16. So now I only have 4 left. Now carbon's octets are all satisfied, hydrogens are all satisfied, but not oxygen. So I'm going to put those last 4 on the oxygen here. And then that way we don't have any formal charges because that oxygen is making 2 bonds. Okay, the shape of this is going to be tetrahedral. So this is what we've got here. We've got one lone pair here and another lone pair here. This is our central oxygen. And then this guy is one CH3 and this guy is the other CH3. Okay, so think of that CH3, that's called a methyl group. Think of it as kind of one unit. So the hybridization that's going to be associated with that, since this is tetrahedral, we need sp3. That adds up to 4 domains. And with 4 domains, we expect the bond angle to be 109.5 degrees. And the shape on this is going to be bent. And that's because we have these 2 lone pairs here. Remember, the shape is only based on the parts that we could see, the atoms, not the lone pairs.